Hello and thanks for joining. My name is Dougal Tomorrow. I've been at Atlassian for almost 4 years and in the ecosystem team for about 2 years. Today I'm going to run through some changes we've been making to Connect that allow app iframes to be cached by the browser. In terms of our agenda, I'll start with a brief outline of app rendering. I'll then describe the problem we're addressing. A lot of the talk will be spent explaining the solution and various considerations. I'll hopefully have time to run through a demo and then wrap up. Not long ago, I opened the DevTools in Chrome, disabled caching, and loaded an issue page. The initial HTML document took nearly 6 seconds to load, whilst all the page's resources took about 12 seconds to load. The issue page had an app on it called My Reminders, which was developed by a colleague of mine. He's taken care to make sure it's hosted well, but it still took a few seconds to load. So the first point I want to make is that loading content over the internet is expensive. Now let's take a look at the way a user expects our products to behave. When a user navigates to one of our products or navigates between major views in our products, they perceive this as a full page load. These days, they expect page loads to be fast. However, users expect minor operations within a view to be instant. The user doesn't care that under the hood there's an iframe being created for an app which requires a whole lot of new resources to be retrieved and rendered. For example, this is what a user typically sees if they open a dialog with content served by an app. Notice the delay between the construction of the dialog and the loading of its content. Users would typically expect dialogs such as this to open instantly. Here is a simple survey of types of web applications for the purpose of this presentation. In particular, I'm interested in pointing out their cacheability. I'm defining cacheability as being able to provide an initial user experience without network loads. The first row corresponds to static apps, which are pre-built and have no dynamic content. Web apps such as these are easily cached by browsers. The middle row corresponds to traditional server-side generated apps, which often use URL parameters to receive information. All the processing occurs in the server, and these apps are difficult for browsers to cache. Lastly, there's client-side single-page applications. These web apps typically render a cacheable shell quite quickly and then progressively render dynamic content. These are cacheable because a fast initial user experience can be served by the browser cache. So putting together the previous slides, this talk presents new Connect APIs that will allow cacheable apps to load much faster than they do today. In fact, with a few changes to apps, many app iframes will start appearing instantly, which is what users expect of a modern web application. It should be noted, however, that taking advantage of these APIs will be easier for some apps than others. It depends on the architecture of the app and specifically its cacheability. Alright, now we have a shared understanding of app rendering. Let me explain a specific problem in Connect that we've been focusing on. Let's say you're writing an app which needs to embed some content into Jira or Confluence. The light blue rectangle at the top represents Jira or Confluence in your browser, where the inner green rectangle is an app iframe. Connect has several modules that render iframes like this. To render an iframe in Jira or Confluence, the app declares a module in the app's descriptor, like this. The example here declares a page module, but iframes are also used for other modules such as web panels, dialogs, and Confluence dynamic content macros. Now let's compare the URL in our descriptor with the URL that Connect generates the app's iframe with. As illustrated here, Connect adds query parameters to the URL. And not just a few query parameters, a lot. This shows what a typical app iframe URL really looks like. All those dynamically added query parameters prevent the browser being able to cache the page being served. That might be reasonable for traditional server-generated web apps we identified earlier as not being cacheable. However, Connect is getting in the way of web apps that are cacheable. So what's the solution? Getting back to our illustration, the obvious solution is to stop connect adding query parameters to iframe URLs. But apps are expecting these query parameters, so this isn't backwards compatible. So we need to let apps opt in to receiving unaltered iframe URLs. Apps can now do this by adding a declaration in their app descriptor that indicates the iframe resource is cacheable. So if the app sets the cacheable option for a particular module, this is what happens to the corresponding iframe URL. Obviously, removing all the extra query parameters makes it a lot more cacheable. So just to be clear, if the module is declared as cacheable, the iframe will get exactly the same URL declared in the app's descriptor. No extra query parameters are added by connect. And here is a side-by-side comparison showing the effect on a demo app. The times at the top shows how long it takes to render the app's dialog. The left is non-cacheable, whilst the right is cacheable. Of course, the impact on any given app will vary since it is dependent on the architecture of the app and how it is hosted. So after declaring the module as cacheable, the module's iframe can be cached, but it doesn't have access to all those query parameters. In summary, we've made it faster, but lost functionality. Let's explore how we fix the problem of the app not having context. We'll start with identifying some very specific context parameters. Connect provides a script called all.js, which allows it to inject APIs into the app iframe. The app determines the location of all.js using query parameters. For example, the XDME query parameter identifies the current Jira or Confluence tenant URL. If the query parameters are removed, apps will no longer be able to determine the location of all.js. We've solved this by hosting all.js on a CDN with a simple fixed location. This means the iframe query parameters used to identify the location of all.js are now not necessary. Let's compare the methods for identifying the location of all.js. The fixed URL has a few advantages. It's easier to code because it allows a static script tag to be added into the page rather than dynamically generating one. The fixed location is hosted by a CDN, which means it will be physically closer to the browser and there'll be less latency. Being CDN hosted also means faster SSL and DNS resolution. Let's dig into some details about caching and versioning of all.js. When loading all.js using a tenant URL, the version served by the tenant naturally matches the version of the host product, Jira or Confluence. Deploying a new version of all.js always coincides with deploying a new version of Jira or Confluence. However, this simple approach means that the cache period can't be long. At the moment, the cache period is half an hour, so it's possible for browsers to be using the wrong version for half an hour after a deployment. With the fixed location of all.js, we wanted to provide longer cache times, but still be able to publish new versions of it. We've achieved this by making the all.js referenced by apps actually what we call a loader script. It works out what the current version of all.js is and uses this to construct the URL to the real all.js. It then loads the real all.js into the apps page. This approach allows the loader script and all versions of the real all.js scripts to be served with very long cache times. I was told never to present a wall of code on any slides, but hey, this is the advanced track, right? This is the all.js loader script. The constant at the top identifies the domain hosting all.js. Amazon CloudFront and S3 are used for hosting. Notice the use of window.name to find a parameter called crev, followed by a version. The version after the crev field identifies the version of all.js to load. The domain and version are merged together to form the full URL of the real all.js to load. Notice the false parameter here. This means the request to load all.js is done synchronously. Since the loader script loads the real all.js, just put it above your other scripts and everything will work fine. You shouldn't have to worry about all these details, but if you look into your browser's dev tools, then knowing how this works might prevent you from becoming confused when you see two all.js scripts have been loaded. So going back to our comparison, cacheable iframes load faster and the app can load all.js from a fixed location. However, there are other context parameters that used to be sent in the app's iframe URL that are no longer being sent. For example, the app won't know what the current Jira project is. Most apps need to be able to get its context in order to be useful. Let's now solve the problem of apps not having context. Instead of the context being pushed to apps using query parameters, new APIs have been created allowing apps to pull context from the product. The first method to get context involves retrieving a JOT, or a JSON Web Token. JOTs retrieved using this API will contain a context object in a JOT claim called context. You'll need to decode the JOT on your app server using your app's shared secret in order to access the context. The second method to get context results in it being directly accessible to your app's JavaScript. In this example, an issue ID in the context is being used to make a REST call. So why do we need two methods to get context? Basically, it's because code in the browser can be modified by the user and therefore shouldn't be trusted. Firstly, if you just want to display some context values such as the Jira issue key, you can use the getContext method. Next, if you want to use the context to send a request to the host product, then you can also use getContext because the product will authorize the request. If, however, your app needs to perform an operation on its server, then the context should be passed to it securely. This means you must use the getToken method. Let's take a look at the context objects. The context object returned by getContext is the same as the context claim of the JOT returned by getToken. The structure of the context object looks something like this. The context object has product agnostic fields and also a product specific field. Remember how context parameters are specified in app descriptor iframe templates? To specify a Jira project ID, you would add a context parameter project.id to the module's URL template. When implementing this new context structure, we figured there was no need to be consistent with the way context parameters are specified in URL templates, so we've gone for a hierarchical structure such shown as here. Okay, so let's recap our solution. Firstly, we allow apps to declare modules as being cacheable, so Connect doesn't add iframe parameters. Second, we provide a fixed location for all.js to make some of the Connect query parameters obsolete. Lastly, we created new APIs so that the context can be retrieved by the app. So here's a final look at our comparison. Declaring the app module as cacheable allows it to be loaded more quickly and now without losing any functionality. Okay, so there are some other considerations also worth talking about. Actually, there's quite a few considerations. Before digging into some of the details, here's a simple component diagram providing an overview of Connect. Connect has a client-side component called ACJS, which is short for Atlassian Connect JavaScript. The Connect plugin comprises Java code which provides the product with everything it needs to know about what apps are installed and what their features are. There are times when ACJS needs to query the Connect plugin in order to find details about an app module. For example, when an app sends a request to open a dialog module, ACJS needs to resolve the module by calling a Connect component called the content resolver. Calling the content resolver in the middle of UI interactions results in a slow user experience, so we're making optimizations to avoid this in certain cases. For example, we expect most apps to retrieve context when they first appear, so we load the data into the client ahead of time. When your app requests context, ACJS first checks its cache to see if it is already present. The cache has a short expiry time, but it is long enough to handle apps that call it excessively. We don't want to cache context too long since the data can become stale. We've also made some improvements to the way in which web items work. Up until now, when you clicked on a web item, ACJS would first need to resolve the target of the web item so it knew what to do with the click. But now we're encoding details about the target into the web item, which means there's no need to make a call to Jira or Confluence after the click. This works for web items where the target is dialog or inline dialog. The best part of this is that all apps get this for free. You don't need to make any changes to your app. Okay, so let's move from web items to a technique called prefetching. Say your app has a panel that can open a dialog. Your app panel can include a prefetch link, which instructs the browser to load the app dialog resource. This ensures that by the time your user performs whatever action is necessary to cause the dialog to be opened, your browser has already fetched and cached the dialog resource. This technique is only possible now that we support cacheable app frames, since before it would be impossible to add links to the page with all the necessary query parameters. And this is all it takes to prefetch an app resource. Link prefetching is pretty simple and there's no downside since the browser only does the prefetching during idle time. When you start opting into cacheable iframes, be aware that we've updated the parsing of app descriptors so that setting the cacheable option and providing context parameters in the URL are mutually exclusive. This is an example of an invalid descriptor. Note that you can still add query parameters to your URLs, you just can't add context parameters. The JOTs returned by the new getToken JavaScript API are slightly different to the JOTs used elsewhere in Connect. For example, the JOTs that sign connect non-cacheable iframe URLs with. Let's compare the differences. Here's a comparison between the two types of JOTs. The context claim in the JOTs returned by getToken has been expanded to provide the information that apps use to be able to request in app descriptor URL templates. For example, a Jira app will be able to retrieve the details about the current project. Context JOTs also don't have a query string hash claim. This is because context JOTs are not tied to any particular URLs, so there's also no query string applicable to them. Connect still creates standard JOTs with a QSH claim, so apps still need to validate it. In addition, apps still need to create JOTs with QSH claims when calling the product. Context JOTs also have a longer expiry time. The expiry time is fairly arbitrary, but we felt relaxing it to 15 minutes would result in fewer problems caused by clock skews and excessive delays before app server processing. If your app is built on top of our client frameworks, you should ensure that you are using these versions or later to ensure they accept JOTs without QSH claims. If your app isn't built on our client frameworks, then just make sure that your app will accept JOTs without QSH claims. You should be careful before setting long cache times for your app iframes. This is because you need to be able to push out fixes reasonably quickly. For a normal web application, you can publish a new version of the app with different URLs, which forces the browser to fetch new versions. A versioning scheme like this allows your app to have very long cache period times. For Connect apps, however, app iframe URLs are defined in the app descriptor, so this requires the version in Atlassian Marketplace to be updated. The problem is that app updates in Marketplace take about 6 hours to roll out, so you need to be careful what resources you set long cache times to. With the app shell architecture, the shell of the application changes rarely, yet still provides the initial rendering, so you're probably safe to set a long cache time on the app shell. Currently, these modules can be declared as being cacheable. The context objects returned by the new APIs don't yet have attributes specific to Service Desk and Jira software. So for example, your app won't be able to determine the current board ID or sprint ID. There's no reason they can't be added, but there just hasn't been time to implement the functionality yet. The page module allows apps to define their own context parameters. The context object returned by the new APIs does not support app-specific context. It is, however, possible to add support for this in the future. There is currently no global app descriptor property allowing an app to opt in for all modules, although it might be something we can add and introduce later. Let's move on to some recommendations. I would recommend you start loading all.js from our CDN because it's easier to code and your app will get a little performance boost. As mentioned before, make sure you add your other script tags after all.js so that they are loaded in the correct order. This way, your app script can immediately start referencing the global API object provided by all.js. The problem with synchronously loading scripts is that it blocks page rendering. For this reason, you might like to load your app script asynchronously. ACJS renders a spinner like this whilst your app iframe loads. All.js fires an event causing the spinner to disappear, so delaying the execution of all.js will also delay when the spinner disappears. Given this, you should be careful if you do anything to delay the loading of all.js. Getting back to our script tags, you could use the async property when loading all.js. This will unblock your app's rendering, but the spinner will also be visible longer. There's also no guarantee that the global API object will be immediately available, so I wouldn't necessarily recommend this approach. Another option is to asynchronously load all the scripts using the defer attribute. The defer attribute guarantees script execution order, but it's delayed until the HTML parser has finished. Although it will work, I wouldn't recommend this approach either, since the removal of the loading indicator will be delayed. Okay, changing to use the CDN version of all.js was easy. What about declaring modules as cacheable? Remember, cacheable app iframes is a new feature that is not backward compatible with previous behavior, which is why apps must opt into the new behavior. We've deliberately made the opt-in mechanism work on a module-by-module basis to allow you to take an iterative approach and reduce risk, so I would suggest migrating one module at a time. You should probably start with the easy wins. For example, does your app have a simple static dialog that isn't dependent on context? Maybe you've got a confirmation dialog or a dialog that presents some basic information. Obviously, make sure that your module is not dependent on functionality that is not yet supported, such as app-specific context. Okay, demo time. This is a simple web application that I've developed to illustrate some of the benefits of cacheable app iframes. At the top left, we have some configuration information. At the bottom left, we have a simulation. At the top right, we have a component diagram, and at the bottom right, we have timing information. Okay, so let's look at the first scenario where an app panel creates a dialog using ap.dialog.create. The scenario starts where the user triggers an event within the app panel. This event causes the app panel to create the dialog, which is sent to ACJS. ACJS then has to resolve the dialog module to work out the details of the dialog of the target of the create call. Once this is done, ACJS injects the iframe content into the page, which causes the web browser to go and fetch the app dialog resource. Once this is done, the web browser can render the dialog. And so this is what the simulation of that looks like. You see the familiar delay when you before the content of the dialog is visible. Okay, so let's declare the dialog as being cacheable now. So what we can see is this step 4, the fetching of the dialog, collapsed because it has previously been cached by the web browser. So this is what that simulation looks like. You can see the loading spinner was still visible, but it was there for a shorter time. Okay, currently we have an open issue in our backlog. It's currently being worked on, whereby we are going to pre-resolve cacheable URLs. So let's enable that option. This is a future state which we can expect to see. You can see here that the cacheable iframe has been loaded almost instantly. Okay, let's take a look at another scenario, a web item targeting a dialog. In this scenario, the user, and we're going to assume the normal case which we expect, where the user clicks the web item after the context has expired. The scenario starts where the user clicks on a web item. The web item click is sent over to ACJS. ACJS needs to, at this point, to refresh the context because it has a context jot in its in the target of the web item that is now become stale. Once the context has been retrieved, ACJS inserts some iframe code into the page, which causes the browser to fetch the dialog iframe resource. Once this is done, the browser can render the dialog. Now let's assume also in this scenario, the app dialog context is necessary for the dialog to display. So the dialog code gets the context from the query parameters. That's because this dialog is not cacheable. And finally, the app dialog can display the context information. All this takes about 1.3 seconds. Let's see the simulation. You see a very large delay that processing the web item click and then fetching the dialog resource. Okay, so let's now make this app dialog cacheable. You can see what's happened is a lot of the activity has been deferred to after the dialog has been displayed. So in this case, the user again starts by clicking on the web item. The web item click goes to ACJS, and this time ACJS doesn't, at this point, have to go to the content resolver because there's no stale information in the web item that needs to be updated. And at this point also, when ACJS inserts the iframe code into the page, there is no need for the browser to make a network call because it's already got the dialog iframe resource cached. The dialog can then be rendered. And now here is the difference. Because we've got the dialog as being cacheable, the only way to retrieve the context information is by calling ap.context.getContext. This is where the only network call gets made. This is where the ACJS has to go to the content resolver to get fresh context. And finally, the context information can be displayed within the dialog. Let's have a look at what that looks like. So you can see there was a very short initial, the dialog was basically rendered instantly, but then there was a little spinner within the app panel whereby when it was waiting for the dialog context information to be retrieved. Let's compare the two methods. We've gone from this, where there's this initial large delay and a poor user experience, to this, which is much more acceptable. If, however, the user clicks on the web item after the context is expired, all the information there was actually no network calls anywhere in any of this. But yet still, if the dialog is cacheable, there will still be a network call because the dialog resource has to be refetched. So in the not too distant future, clicking on a non-expired web item should appear instantly. Our final scenario explains the prefetching link. This scenario is a bit of a combination of loading an entire product resource and with a cold cache, and then combining the previous scenario of creating a dialog programmatically. This scenario only makes sense for cacheable dialogs, since it is impossible to prefetch a non-cacheable dialog. Okay. I've also created a Connect Demo Cacheable iframes app. You can clone this at Bitbucket at this URL. This is the connect descriptor. You can see I've declared cacheable true in certain locations. I've got a cacheable form of the dialog, and this form of the dialog is non-cacheable. I have a dynamic content macro, which is declared as cacheable. The viewer is declared as cacheable, and so is the editor. And then there are a bunch of web items. Okay, so this is what the app looks like in Confluence. This is a page view served by the app. We'll scroll down. You can see here it's made a call to ap.getContext, and here's the context information returned in this case. It's also retrieved a JSON web token using the getToken method, and then it's displaying the current URL. At the top is timing information, and a little bit more detail is provided when the dialogs are open. So I'll open the dialogs now. First, we'll start with the non-cacheable dialog. You can see here a large delay in going to the server. In this demo app, there's an intentional delay in the server to make the server hits obvious. You can see here that it's only a short time since the page was rendered in the server, which indicates that it wasn't cached. Conversely, it took a long time for the actual panel to create. Here it's being measured as the time difference between the actual call to create was made and when the actual content on the page was created. And again, we have the same sort of information, but you can see here the current URL of this page is the non-cacheable URL. Okay, so let's compare this to the cacheable dialog. There you can see it opening a lot faster. And you can see that the number of milliseconds since the server render was very large. Yeah. That indicates that the page has been cached. Also, we have the end-to-end timing, which it took less than a second. Again, we have the context information and the token, and this time we see that the actual current URL is that simple form, which is why the browser was able to cache it. Okay, so this is a Confluence page macro. Let's open up the macro and edit it. Here's the item. Now notice here that the editor is spent a long time in the open mode. That's because the editor wasn't cached by the browser. Now it should be cached, so let's try and open that again. You should see that the editor loads the view much more quickly. There we go. It loaded a lot more quickly, and it's been 22 seconds since the content was served. Since the browser had basically cached the content. And again, this is the current URL showing the simple form that is cacheable by the browser. Okay, so let's publish this page. And we should notice that the page appears quite quickly. The content of the page appears quite quickly. In fact, it's been 1037 seconds since the browser fetched this resource. Okay, so this is the same app installed into Jira, and here we can open the Cacheable Apps panel. At this point here, at the time this panel was rendered was only 534 milliseconds since the page was rendered. Let's load the page again to see if it's been cached. So here we are. We reload the panel will have been cached. Again, it's 1072 seconds since the panel was retrieved. So the browser's using that prefetched version or cached version of the panel. And so again here we see the same sort of information, and we see that in this time we also have the simple form of the URL. Notice here that I've just provided a query parameter to compress some of the information in this panel view. And again we can open the dialogs to demonstrate the cacheable attributes. And notice here that the context information now is showing Jira information, of course, since we've got it installed in Jira. And finally, I'd like to point out the Cacheable app iframes guide. It's an all-in-one guide taking you through the details of how to get started writing cacheable apps. You should be able to find it in the sidebar in the learning section. I'm going to sum up by identifying a few resources where you can find more information and explore at your own pace. If you're interested, you can visit and play around with the timing scenarios application at this location. The demo app is based on the Atlassian Connect Express client framework. You can clone it at this location. The last resource is the user guide available in our developer docs. Okay, thanks very much for your time. A special thanks also to Chris Whittington and Einar Pearson, who did a great job designing the new APIs and implementing the functionality. Without them, this would never have been possible. Thank you.